Okay, let's get started. This is section 7.5, conditional probability, video number 2. So we're doing conditional probabilities. We're just taking a look at some more examples. All right, so here we go. First one reads, our experiment is that 2 cards are drawn from a deck without replacement one at a time. Okay, so our experiment is to pick 2 cards from a deck one at a time. Find the probability that the second card is red given that the first card was red. So I'm going to highlight a couple things here. Second card is red, first card was red. So I've got an experiment. My experiment is to pick 2 cards, one at a time, and I'm doing this without replacement. Right? My sample space then is all 52 cards. My event E is going to be an event that the first card was red. F is going to be second card red, and then they want us to calculate the probability of F given E. Okay. Well, I know that that's going to be the probability of F intersection E divided by the probability of E. So I'm going to go ahead and do some calculations over here on the side. Let's see. The probability of E, I'm going to do the denominator first, is going to be that the, let's see, first card was red, so that's going to be 26 red cards, 52 cards in the deck. So 26 out of 52, which I believe reduces down to 1/2. Okay. I also need the probability of F intersection E. That is the probability that both cards are red. Probably of F intersection E, both cards are red. Oh, so let's see, how are we going to figure that out? Both cards are red. Okay. Let's see, there's 26 cards in the deck, both cards red. Well, maybe I could use a tree diagram to help me with this. Like I could draw one of those tree diagrams, and the first card could be red, or the first card could not be red, and then the second card could be red, or the second card could, not be red, or the second card could be red, or the second card could not be red. But technically, these are actually conditional probabilities, because they are saying that the second branch depends on what the first branch was. And so if I know that this is 1/2, and then that it would also be 1/2, because just if the first card is red or not red is there. This branch right here is actually the branch that I'm trying to find. And so while, yeah, I can use formulas for this, sometimes using those formulas actually isn't the easiest way or the most intuitive way to make this happen. I can just look at it just right here and think about what's happening. Now, I'm going to rewrite this for a second as 26 out of 52. And the reason I'm going to do this, I'm going to use that to help me talk about this next probability here. All right? If I make it to here, that means that the first card was red. That means that the deck of cards has been reduced by 1 because I'm doing it without replacement. And now there are only 51 cards left in that deck. And that first card being red means that there are only 25 of those cards left in the deck that are red. So the conditional probability, the probability of the second card being red, given that the first card was red, is actually going to be 25 out of 51. So what I'm getting at here with this problem is conditional probability is an important thing. It's an important idea. How you calculate it really depends on what information you're given. If you are given enough information that this formula makes sense, that is, that you have these probabilities at hand that you can easily calculate, then use that formula. If you're given information so that you know the new numbers of these things, the number of outcomes in these events, if you want to get fancy about it, then use the numbers one. But if I'm in a situation where I don't have numbers for this, and I don't have an easy way to calculate that probability, well, I could set up a tree diagram and look at what's happening and kind of reason through it and still come up with the correct answer for the probability. Right? So there's many ways to do this. You just got to find a way that works for the information that you've been given. Okay? Let's take a look at this next example. It reads, find the probability that the second card is a face card given that the first card was a 9. Okay, so I'm going to say that, I don't want that. I'm going to say that the E is going to be the event that the first card 9, F is going to be the event second card face card. And then what I'm going to do is I'm just going to draw that tree diagram again because I thought that was pretty easy. So my first card here, it's either going to be a 9 or not a 9. And then my second set of branches is either going to be a face card given that it was a 9 or not a face card given that it was a 9. And then these branches down here would be face card given that it was not a 9, and this would be not a face card given that it was not a 9. But this is the branch that we care about. So I'm not even going to bother with this one or this one or this one, and I'm just going to tell you that these two down here are really, really hard to calculate. The reason they're really hard to calculate is, what if this was a face card? How would that affect this? And what if it was not a 9 but also not a face card? So that's a more complicated problem probably for later. Okay? We're just going to look at the one we care about. All right, so I'm going to take a look at the branches here. This first branch over here that I care about, this 9 getting to here, is going to be 4 out of 52 because there are 4 9s in the deck, 52 cards in the deck, so it'd probably be 4 out of 52. I know that reduces. I'm just not going to do it. Okay? Now I'm going to move on to that green branch right here, the one I actually care about. Right? Now, given that the first card was a 9, I know that all 12 face cards are still in the deck. But given that the first card was a 9 and we pulled it out, I know that there's only 51 cards left in the deck. So that conditional probability of the face card given the 9 is 12 out of 51. So the probability that they want me to calculate, which I'm calling F given E here, or face card on the, face card on the second, given that the first was a 9, is going to be 12 out of 51. All right, more examples. In a room where 40% of the people are adults and the rest are children, 25% of the people are drinking a soda. Find the probability that a randomly chosen person is an adult given that they are drinking soda. Okay. Find the probability that they are an adult drinking soda. So I'm supposed to find the probability of adult given soda. Okay? Soda, soda, not. 0.25, 0.75. Adult given soda, not adult given soda. Adult given not soda. What's that going to be down there? That's going to be not an adult given not soda. 40% of the people are adults. So 0.4? Would that make sense? I don't know. Is there a 40% given they're drinking soda? Maybe I need the formula for this one. So what would the formula look like? Well, the formula would say that this can be calculated by finding the probability of adult intersection soda divided by the probability of soda. I don't know how to do that one either because I don't have this. This is a complicated problem. Maybe I need to use numerical values for this. Okay, so how am I going to work this one out? I think I know what to do now. Okay, since this isn't working for me, this formula one isn't working for me, and since this tree diagram, I'm not sure I feel comfortable with this, I'm going to go to numbers. So let's just pretend for a minute that there were 100 people in this room, right? So that would mean that if I make this set be the adults, that the number of people there needs to be 40. And if I make this set be the set soda drinkers, then the number of people on that set needs to be 25. And that this piece right here in the middle is going to be the intersection of those two sets. And so how many people are going to be in there? Well, there's going to be 10 people in there. And how to come up with that? Well, if a quarter of the people, if 25% of the people are drinking soda, and there's 40 adults, then a quarter of those would be 40. This would be 30. This would be 15. And out here, this is going to be 45. So now what I can do is I can go ahead and try to figure out what's going on with my probability that I'm trying to calculate. So since this tree diagram didn't help me at all, I'm just going to go ahead and get rid of it. And I'm going to say that the probability that someone is an adult, given that they are drinking soda, is going to be 10 out of 25, which reduces down to, what is that? That's going to be 2/5. Okay. What's the probability that they're an adult drinking soda? All right, now here we're going to get into that question of how do I know when it's conditional probability and how do I know when it's not? This one was conditional probability because it has that classic given that statement. The idea that two things are happening in sequence. Right? This second one doesn't talk about anything but sequence. They're talking about finding the probability that someone is just an adult who is also drinking soda. Meaning we're looking for the probability of a intersection S. We're looking for this probability right here that we didn't know before. That's what we're trying to find. And so what we're going to do is we're going to go back to this little diagram I made over here, this Venn diagram over here. And we're going to say that there are 10 people who are adults who are drinking soda, but there were 100 people in the room because we have not reduced our sample space from the original 100 people that we put in the room. Okay? And so we would get 10 out of 100 or 1 out of 10. Now I know what you're thinking. Well, wait a second. You made up this number 100. So if I use a different number, would I get a different answer? Well, what if you had used 200? Well, then that would just be 80. That would just be 50. This would just be 20. That would be 60. That would be 30. And that would be 90. Your calculation down here would now be 20 out of 200, but it still reduces down to 1/10. All right, I'm going to end this video here. We'll come back and do the product rule in the last video for the section.